Hello APC Mechanics students on Unit 7 in Gravitation in Class 6, 7.2 Orbits of Planets and Satellites, Part 2. Then Section 1, Kepler's laws for planetary motion. Kepler's introduced three laws that has to deal with the motion of planets around the Sun. Then let's start with the first law, known as the law of orbits. The orbits of planets around the Sun are elliptical, with the Sun being located at one of the foci. So that's the orbit of the planet. These are the two foci of the ellipse. Recall that the ellipse is a stretched circle, and the planet, the central mass would be located at one of the foci. Previously, we have worked with the planetary motion as if they occupy perfect circular orbits, but we have explained that that's not the case. And in most of the cases, the formation of the orbits are elliptical, and in the next section we will explain why. So in the case, if we're working with elliptical orbits, the central mass would occupy one of the foci. So that's the first law. Now the second law is the law of areas. A radius joining any planet to the Sun sweeps out equal areas in the same amount of time. Now let's assume another position for the planet, and this planet will move from the point A to the point B in a time interval delta t. In this case, there is an area A1 swept along this motion for a time interval given by delta t. Now assuming two another positions given by, let's say, for example, B and C, for the same time interval delta t, there will be another area A2 swept. The thing is that if the time interval delta t is the same for both displacements, then the area A1 would be equal to the area A2, and this is not a very straightforward result. Why? Because we know that as the planet is moving around this elliptical path, the speed is not constant. However, there is a conserved quantity, which is the area swept, and this can be derived using the conservation of angular momentum and a universal law of gravitation. Now, what about Kepler's third law, which is the law of periods? The ratio of squares of the periods of revolution around the Sun of any two planets equal to the ratio of the cubes of the semi-major axes of the respective ellipses. This can be easily understood by that the square of the period t square is proportional to the cube of the radius r cube. Now let's recall for a circular orbit we have that t square is proportional to r cube, in a sense that t square is equal to 4 pi square r cube over gm. Now this is a constant, which means that t square is equal to a constant multiplied by r cube, which means that t square divided by r cube is equal to the constant. For this reason, Kepler's third law states that the ratio of square of the periods of revolution around the Sun of any two planets equal to the ratio of the cubes of the semi-major axes of the respective ellipses, which means that briefly t square over r cube is equal to a constant, and this is a conserved quantity. Now, although this result holds for circular orbits, but it can be generalized for elliptical as well, which means that t square is proportional to r cube. Although the above relation holds for circular orbits, but the proportionality between t square and r cube holds also for elliptical orbits. Now, let me mention a very important remark. Kepler's laws for planetary motion are specifically formulated to describe the motion of massive objects around a central body, like a star, for example, considered to be much more inertial. These laws, they work perfectly whenever we're talking about the motion of two massive bodies, such that one of them is a central mass, very inertial, and the other one is less inertial, and it's orbiting the central mass. However, they are not directly applicable to the relative motion of two stars, known as a binary system. If we're talking about the motion of two stars, that their mass are comparable, such type of systems are known as a binary system, and we cannot apply Kepler's laws of motion. They only work whenever we're talking about planets or satellites in motion around a central mass, which is much more inertial. And now the final section for this unit, which is section 2, formation of orbits. Given a massive object of mass m, like a satellite for example, to set the satellite into a desired circular orbit of separation distance r around the central mass m, a certain speed is required. This speed is given by the square root of gm divided by r in a direction perpendicular to the pull of gravity Fg. So we have determined this speed using Newton's universal law of gravitation and circular motion. And indeed, to set the satellite in a perfect circular orbit around the central mass, it should be given this speed. Along which direction? Now the pull of gravity would be directed toward to the center of the planet. Then the velocity should be given exactly in this direction, or in that direction perpendicular to the pull of gravity, which is the acceleration, in order to form circular motion. This is how circular orbits are formed. But the thing is that it rarely happens that the satellite is given the exact amount of needed speed to form such circular orbits. If you think about it, it's very challenging to calculate this V and to inject to the satellite this amount of speed. And here we can differentiate between two cases. The first case, if that you give a satellite a tangential velocity, so we're assuming that we're already giving a tangential velocity, but the thing is that the amount of speed is greater. The satellite is given a tangential velocity that's slightly faster. Now in this case, instead of the orbit being circular, the orbit of the satellite would be elliptical outside the circle with a major axis SP. Now if it happens that we launch the satellite here with a certain velocity, either up or down tangential to the trajectory or to the pull of gravity, perpendicular to the pull of gravity, if the amount of speed injected is greater, that would give us an elliptical orbit which is outside the circle. But the thing is that SP would be the major axis of the ellipse. And now if the satellite is given a tangential velocity that is slightly slower, here also let me mention that in this case the planet would also occupy one of the foci. Now if the satellite is given a tangential velocity that is slightly slower, suppose now we inject for the satellite an amount of velocity in the same direction which is tangential, but the value of the speed, or the value of the velocity, which is the speed, is slightly slower. In this case, the orbit of the satellite would be also an ellipse, but contained inside the circle, with P being one of the foci, and SP would be again the major axis. Then briefly, in order to form circular orbits, this amount of speed exactly should be given, but this rarely happens. Sometimes we give more speed or less speed. More speed would give us an elliptical orbit outside the circle with SP to be the major axis. Less speed would give us an elliptical orbit again, but inside the circle with SP being the major axis. Now for the rest of the video, we're gonna solve some exercises on what we have explained so far in this unit. A small rock is launched straight upwards from the surface of planet with no atmosphere. The initial speed of the rock is twice the escape speed VE. Now let's recall what is the escape speed VE. It is the amount of speed given to an object in order to make it free from the planet, and the final kinetic energy in this case would be 0. If we're given the rock twice the escape speed, so it will still escape the planet, but the thing is that the final kinetic energy won't be 0 because we have excess of energy. If the gravitational effects from the other objects are negligible, the speed of the rock at a very great distance from the planet will approach a value, so we need to find the final speed, and this can be determined using conservation of energy. So let me say energy initial is equal to energy final. Now energy is about kinetic and gravitational potential energy. Similarly here, kinetic energy final plus gravitational potential energy final, that would be 0 because at a very large distance we would lose the bond. The initial kinetic energy of the mass of the rock is m. That would be half m, the double of VE to the power of 2, minus a g m capital M divided by r, in which m is the central mass and small m is the mass of the rock. That would be equal to half mv square final, and we're interested in determining v final because initially the rock has been given a speed which is greater than the escape speed given by the twice the escape speed. Now we can directly cancel the masses. Recall that the escape speed is given by the square root of the double of g central mass divided by r, so that would be half 4. Now the power 2 cancels the radical, that would be 2gm divided by r. Now 2 with 2 cancels, minus gm divided by r is equal to half v square final. Now 4gm over r minus gm over r, that would be 3gm divided by r, is equal to half v square final, which means that v square final is given by 3 multiplied by 2gm divided by r. Now why I have done the following representation? Because we need to express our answer in terms of the escape speed, And if we do the square root, then Vf would be the square root of 3 multiplied by the square root of 2gm divided by r. Now this is the escape speed, so that would be radical 3 Ve, and the correct answer is given by E. Now a new planet has been discovered, and given the name Planet X, the mass of Planet X is estimated to be 1/2 that of Earth, and the radius of Planet X is estimated to be twice that of Earth. The estimated mass of the planet and radius of Planet X are used to calculate the minimum escape speed Vc for an object launched from the surface of a planet. If the actual mass and or the radius of the planet are slightly different from the estimated values, how will the actual speed Va for the surface of Planet X compare to Vc? So based on our estimations, we have determined Vc, but the thing is that the actual speed Va, which is the escape speed, is given by Va, and remember that the escape speed is given by the square root of 2gm divided by r. We need to determine how Va is compared to Vc based on the given reason. They're telling us that based on what? Based on the mass of the planet and the radius of the discovered planet. Now Va is equal to Vz regardless of any difference in mass or radius. This is wrong because we know that the escape speed depends explicitly on m and r. Now Va is greater than Vc is if the actual mass is greater and the actual radius is less than their estimated values. This is true because notice that if the mass increase, V would increase. If the radius decrease, V would increase again, so that's correct. Now let's check the other responses. V is greater than Vc if the actual mass is less than. No, that's wrong, and the radius is greater. No, because if m decrease, V will decrease. If r increase, V will decrease again, but we want the estimated speed to be greater than the we need to know that the actual speed, or given that the actual speed is greater than the estimated speed. Here we're talking about escape speed, so that's wrong. Now part D, Va is less than Vc if the actual mass is greater and the actual radius is the same as their estimated value. If m is greater, then V should be greater, then the reasoning should be Va is greater than Vc, so that's wrong. And in either telling us Va is greater than Vc if the actual mass is the same and the actual radius is less, so we know that whenever r decreases, V should increase, therefore the actual should be greater than the estimated, so that's wrong again. Now the escape speed for a rocket at Earth's surface is given by Ve. What would be the rocket's escape speed from the surface of a planet with twice Earth's mass and the same radius as Earth? So the mass has been doubled, but the radius stays the same. Now we can apply the factor of change, Ve, which is given by the square root of 2gm divided by r. That would be the radical of 1 multiplied by 1 multiplied by 2 divided by 1, so that is radical 2, and the correct answer in this case would be B. Now let G be the acceleration due to gravity at the surface of planet of radius r. Which of the following is dimensionally? Pay attention, dimensionally, so we need to only worry about the unit. Correct formula for the minimum kinetic energy that a projectile of mass m must have at the planet's surface if the projectile is to escape from the planet's gravitational field. So we need to check the unit of each of the following quantities and see if it agrees with the unit of the kinetic energy. Now kinetic energy is given by half mv square, and the unit would be kilogram meter square per second square. Now here, because we're talking about specific system, the formula of kinetic energy would be different, but the units should be the same because we're talking about a unique quantity, which is energy. Now let's start with the first one, the radical gr. That would be the radical of meter per second square multiplied by meter, which is the square root of meter square per second square, which is meter per second, and this is the unit of speed and not energy. Then we can directly eliminate A. Now what about mgr? That would be kg meter per second square multiplied by meter, which is indeed kilogram meter square per second square. Then B is the correct answer. Now let's check as a good exercise that C, D, and E have the wrong units. Now mg divided by r, that would be kg meter per second square divided by meter, which is kilogram per second square, and that's wrong. Now m, the square root g divided by r, which is basically kilogram, the radical meter per second square divided by meter, which is kilogram radical of 1 over second square, which is kilogram per second, and that's wrong. Now GR is meter per second square times meter, and that would be meter square per second square, and there is a mass which is missing, so that's wrong. Then B is the correct answer. A spacecraft orbits Earth in a circular orbit of radius r as shown above. When the spacecraft is at position P shown, a short burst of the ship's engine results in a small increase in its speed. So initially the spacecraft is at point P and we have injected more speed. We know that in this case the orbit would be elliptical outside the circle, so it's either D or E, but the thing is that the line connecting P and the center of the planet should be the semi-major axis or the major axis, and in this case D would be the correct answer. Now, exercise 6, a satellite S is in an elliptical orbit around the planet P as shown above, with R1 and R2 being its closest and farthest distance respectively from the center of the planet. If the satellite has a speed v1 at its closest distance, so here we have a speed v1, what is its speed at its farthest distance at the radius R2, which is v2? And we know that in this case we can use the conservation of angular momentum, which gives us the following equation: R1 v1 is equal to R2 v2. Now remember, if this is a free response problem, we need to derive this from scratch, starting from the conservation of angular momentum, and we're interested in determining v2. Then v2 would be given by R1 v1 divided by R2, and in this case A is correct. Now exercise 7, a rocket of mass m is launched from the surface of Earth with an initial speed equal to 1/2 the escape speed. Now the escape speed is given by the square root of 2gm divided by capital R, which is the radius of Earth, because we're launching it from the surface. Now notice that if the rocket is given the escape speed, then the rocket will completely lose the bound. But the thing is that we have launched the rocket with half the speed, which means that it will not lose the bound. There will be still gravitational potential energy in the final state between the rocket and the Earth. The mass and the radius of the Earth are given respectively. What's the maximum altitude? And this is very important. Maximum, it means that the final kinetic energy of the rocket is 0, and the altitude they're asking for h, not for the separation distance. They're asking for the distance from the surface of Earth achieved by the rocket, and this can be done using the conservation of energy. Then let me say energy initial is equal to energy final. Now initial kinetic energy plus the gravitational potential energy is equal to the final kinetic energy plus final kinetic energy and the final gravitational potential energy. Now because this is maximum, then the final kinetic energy is 0. The initial kinetic energy is given by half the escape speed, which is half ve square, and initially we have minus gmm divided by capital R, in which capital R represents the surface of the Earth. And the final gravitational potential energy would be minus gmm divided by R plus h. Now why plus h? Because we are at a maximum altitude that we wish to determine. We are interested in determining h. Now m with m cancels. That would be half multiplied by 1/4. Now the radical cancels with the power of 2. That would be gm divided by R. 2 with 2 cancels. That would be minus gm over R minus gm over R plus h. Gm cancels everywhere. Now 1/4 R minus 1/R. So here if we do the common denominator, that would be, or before doing the common denominator, let me say this is 1/4R. 1/4R minus 1/R is given by minus 1/R plus h. Now here if we do the common denominator 4 and 4, that would be minus 3/4. So let me continue here my work. Minus 3/4R equals to minus 1/R plus h. Now the minus sign cancels. That would be 3R plus 3h is equal to 4R, which means 3h is equal to 4 to R, which means that h is given by R/3, and that is 6.4 times 10 to the power 6 divided by 3, and the answer is given by 2.13 times 10 to the power 6 meters, and the correct answer in this case is B. Now, a satellite is in a circular orbit such that it's always directly over the same point on Earth's equator. Which of the following must be true for the satellite? It must have a specific mass. No, the mass of the satellite is not important. The altitude is important for us, and it must have a specific angular velocity. This is true because a change in speed would result a change in the orbit itself, and because you know that it would be elliptical, and the correct answer in this case is D. Now, a satellite is an elliptical orbit around a planet. It's moving at 1000 meters per second when it is 450,000 kilometers from the center of the planet. The satellite's minimum distance from the center of the planet is 20,000 kilometers. What's the satellite's orbit speed at this location? We know that the speed can be determined using R1. V1 is equal to R2 V2, and we're interested in determining V2. Now V2 is given by R1 divided by R2 multiplied by V1. Now this speed is related to this distance. And remember that the distance should be in meters, but here no need to convert because we're gonna use the cancellation effect. Then 450,000 kilometers divided by 20,000 kilometers. Now both kilometers cancels and we multiply it by 1000. Now the speed should be in meters per second. If the final answer is in meters per second, plugging that on the calculator, then it's given by 22,500 meters per second, making D to be the correct answer. Now exercise 10. Before I solve this exercise is related to a previous one that we have solved, and we have found that the central mass is given by 5 times 10 to the power 22 kg. So we need this number that we have determined previously. Astronomers collect data for several moons in orbit around a distant planet. The data collected are the distance between the planet and each moon and the period of the circular orbit of each moon around the planet. The data are shown in the table. Due to experimental error, the astronomers discovered that the data for one of the moons are not consistent with the data for the other moons. Based on the data provided, which moon's data are not consistent with the data of the other moons? Now, if you think about it, we have two columns, one representing the separation distance and one the period, and we know that we have the mass. The period is determined by the square root of 4 pi square r cubed divided by gm, in which m is the central mass. Now we can use the given values in order to check if the period is the same. You can do it for moons. Now already we have used the moon A to determine the central mass, so you can directly eliminate A. You need to check B, C, D or E. I will check D for you and verify that it's not true. We will use this separation distance, which is given by 5.6 times 10 to the power 8, and we will use the central mass in order to determine the period. The period in this case would be given by the square root of 4 pi square multiplied by 5.6 times 10 to the power 8. Now you need to make sure that the distance is in meters, divided by 6.67 times 10 to the power minus 11 multiplied by 5 times 10 to the power 22. Then you will get a number, but this number is expressed in seconds. The thing is that we need the period in month. Then we need to convert seconds into month. So we need to divide this number by 3600 into hours times 24 times 30. So we need to divide the number that we got by the following. The 3600 is to convert to hours. This is for day and this is for a month, and we would get 17.59 months, which is different than what we have, which is 22.6. And you can repeat the calculations for A. Even if you excluded A, you can repeat it for A, B, C, and E, and you can check that you will get the exact numbers here except for one moon, which is D.